Okay, can you see my screen?
Yeah.
It's not clear.
It is still not clear. Is it okay now?
Yeah, it's okay.
Okay, so yes, we are just going through your slides. Okay.
Okay, the basic electronics. Okay.
Yes, the basic electronics. Okay, so it says determine the forward voltage and forward current for each of the diode models. R is close to 1K ohms and V is biased 10 volts. Okay, so he's saying that this R here, this R here is equals 1K ohms, that is 1,000 ohms.
1,000, correct.
1,000 ohms. Are you okay? And the voltage that is used to bias this diode is 10 volts. Okay. So that is what he meant here. And the question is, the tutorial is saying that you should determine the forward voltage and forward currents, forward bias for each of the diode. Okay. Find the voltage across the limiting resistor in each case and assume dynamic resistance is 10 ohms. And assume the diode is a silicon diode. So you have to assume this diode to be a silicon diode. Okay. Okay, good. So now let's check how to go by it.
So please, in this, how do you assume the voltage?
He said find the voltage across the limiting resistance in each case. Assume dynamic resistance. So he's just giving you an assuming resistance called dynamic resistance. Okay. And he has given it to you. That is 10. Okay. It's 10 ohms. And he's saying that this diode that we see, take it that this diode is actually a silicon. There are different types of diodes. We have LED, light emitting diodes, okay? We have LED, that is light emitting diodes, okay? We have ZENER diodes, ZENER.
Okay.
We have ZENER diodes. So he's saying that this diode that you see here, this one, is actually a silicon diode. So that is what he's trying to say. It's actually a silicon diode.
Okay.
Okay, so let's go to the next thing and see how you can. Okay. I'm coming, the next page is not showing. So let me see, let me unshare. And let me come to this side and see why it's okay. By sharing this, all right.
See how it is.
Yeah, you are not seeing now, but just unshare. I'm coming. It was not showing, so I wanted to find out what was going on.
All right.
Okay, so I'm now sharing that. Okay, so the question, this thing that we just saw, okay, it's saying that ideal diode model. So for an ideal diode, the forward bias, this is a forward bias current. A diode can be forward or reverse bias. F or R.
Okay.
Okay, it can be forward or reverse bias. So when you say ideal diode, if you say ideal diode, do you understand what you mean, an ideal diode?
Okay, there's no move. I still my understanding. Something is ideal.
Yes, like ideal transformer. That means it's a model. It does not have a loss. If something is ideal, it means there is no losses.
The losses, yes.
So assuming whatever current that you pass through, because if it's ideal, there is no loss. So assuming whatever current you pass through, there is no loss. You are likely to get all your current. That is why he says it's an ideal. Okay. So if it's an ideal, that means this formula holds. To determine the forward bias, it is IF, it is main bias over R. So let's go back to where we are. Let me show you something. Okay.
Yes, sir.
Okay. So if you check this one, have you seen that this R is in series with the diode?
Yeah.
Okay, so for Ohm's law, if you're looking for something in circuit, if it's direct, then you can say V equals to, we can say,
IR.
yes, V is equals to IR. Very good. So IR. So if you are looking for I means you are making I the subject.
Yeah.
Okay, so if you want I to be the subject, then I will be equals to V over R. Is that not it?
Yes.
So it's the same. Okay, so it's the same procedure. That is what is we are using to find the I forward, which is the forward current. Do you know why this diode is connected in the forward bias mode? If you connect the voltage source, this is the voltage. Okay, let me explain. If you connect this voltage source, have you seen where I've marked red?
Yes, sir.
Good. That is the voltage source. If you connect the positive side of your battery or the voltage to the positive side of the diode, to the positive side of the diode. So if you connect these two, positive to positive and negative to negative, if you do this,
okay,
that is what is called forward biasing. A diode has a positive terminal called the anode. Okay.
Okay. Yes, sir.
It has positive terminal, and this terminal is called the anode.
Okay.
ANODE. Okay. So the positive terminal is called the anode. And the negative terminal is called the what?
Cathode.
Cathode. Very good. So it has only two terminals. And a normal DC battery also have how many terminals? The battery that we use, how many terminals does the battery have?
Positive and negative.
Very good. So it's the same as a diode connection, is that not it?
Yes, sir.
Good. So there's only two ways you can make a connection. It's either you connect positive to positive, negative to negative, or you make a connection this way. You connect positive to negative, then negative to positive. You see that there's only two ways that is possible. Is that not it?
Yes.
Okay. So if you do the red one, this one, which is positive to negative, positive to positive, we call it forward bias connection, F. Okay.
Please come again.
I'm saying that, you let me use the color this thing to show you what I mean. I'm saying that A diode can only be connected positive to positive, negative to negative. Okay, if you do this connection, we call it forward bias, F.
Okay.
Okay, so if you connect positive of your battery terminal to the positive of the diode, which is the anode, and if you connect the negative of your battery terminal to the negative of the diode, okay, then we call it forward what? Bias. Are you okay with that first point?
Yes.
Okay.
Yes, sir.
The next point I want you to know is that I'm using a blue mark for that. If you connect this positive to the negative terminal of the battery, and you connect this negative to the positive terminal of the battery, that means you have cross-connected. You see that blue is crossing.
Yes.
Good. If you have cross-connected, it means that this is what we call it reverse bias. It means you have reversed the polarity. So we call it reverse bias. Are you okay?
Okay.
So we call it reverse bias. So have you seen the difference between forward bias and reverse bias? Have you seen the difference?
Yes.
Yeah.
Okay, very good. So now we can say this diode that we see here, can we say it's forward bias connected or reverse bias connected? Based on what I just explained. Because if you check this line, pass here, pass through the resistor, it goes to the positive side of the terminal. At the same time, this negative line pass here, pass here, and come to the negative side of the terminal. So can we say this diode is forward or reverse bias connected? Which connection
Forward.
is forward bias because it's positive to positive, negative to negative? Are you okay with that?
It's forward.
Good. So you are okay now.
Yes.
So we can apply the same Ohm's law to it because it's a circuit. Okay.
Stop.
Okay.
Okay.
So now let's go to the next case. Okay. So like we were able to deduce. Now we're saying that he's saying that VF forward voltage is 0. For an ideal current, he's saying the forward voltage is 0. Okay. But we are not bothering about the forward voltage now. We are only bothering about the biasing voltage to determine the IF. So to determine the IF, that is forward current, the voltage you must use is main bias and the resistor that was connected, which was the 1K. We said 1K is the same as 1,000 ohms, right? And the biasing voltage was 10 volts. So if you multiply 10 by 1,000, is this 0 will cancel one of the zeros. So it will be 1 over 100. 1 over 100. Can you mute your mic? Abu, can you mute your mic?
Yes, sir.
Just mute your mic. Where you are, there's a noise. Or maybe I should mute everybody so that we can just continue.
Yeah,
Don't worry, let me do it here for you.
So yes, sir.
You can hear me, right?
Yes, sir.
Yeah, okay. Where you
Yeah,
are,
I can hear.
good. Where you are, there seems there's a lot of noise there.
Yeah, I'm here to.
So let's say, let me see. I'm looking for a way to see if I can mute your mic. So can you mute your mic?
Yes, sir.
Let me see if I can. Okay, Abu. So I'm going to, because while you are a little noise, I'm going to mute your mic so that you can only hear me. When you speak, we will not hear. But I will bring it on as a time as we go along, okay? Hello, Abu.
Yes, sir. I can hear you.
Okay, good. So let's continue. Amos, you can unmute your mic now. Amos.
Yes, sir.
Ah, good. It's only Abu that the feed was coming from.
It's in the total.
Yeah. Okay, so let's continue. Let's share. Okay, good. So we are saying that. Can you see the screen?
Yes, sir.
Okay, good. So we are saying that. So this is it. So it means it will be 1/100. So 1/100 will be 0. Because this will move here 1, 2. So 0.0001. Okay. So if you multiply this by 1,000, see that this is M. Is that not it? So it's like this will cancel this. So the 0 will move, it's 1/100. So it will be moving 1 to those. So it's 0.01, not 001. So it will be 0.01. So if you multiply this by 1,000, that means it will move 1, 2, 3. So that will have 10. Is that not it? So that is 10 milliamps. Are you okay? So that is why the answer is, that's why the answer is 10 milliamps. Okay. So that is for that. Then the next question that they were asking us to find was the next question that you were asking us to find. So find the voltage across the limiting resistor. In each case, assume that. So he's saying that we should find a voltage that is across the limiting resistor, meaning that he wants us to find this. Find a voltage that is across the resistor. So meaning we are finding VR, or what is it? So we are finding VR. Okay. Okay. So we are finding VR. Are you okay?
Yes, sir.
Okay, good. So we are finding VR. Okay, that means how do you determine the voltage that is across VR? So that is the one that is going to do. Okay, how do you go by it? Okay. So okay. So VR limits is equal to IF times R limits. All that is trying to say is that if you look at this thing that you are seeing, if you want to find you can see that the diode, we see we are able to find the current that is flowing, the forward current that is flowing into the diode, right? That is IF, which we just found, right? Okay, so because we know that it's a series circuit, so I will flow through it. In a series circuit, the current is common. Is that not it?
Yes, sir.
So if you multiply I by R, you are supposed to get the voltage drop in this resistor. Is that not it? Okay. So now that we understand that one, let's see how to do it. Okay. So you come here. So that is why here he's multiplying IF by R here. Okay. So it is 10 times 10 raised to the power minus 3 amps. So we have 9.3 times, let me see, 10 times 10 raised to the power minus 3A. And we have 1 times 10 raised to the power 3 ohms. Meaning this one is the ohm, that is 1,000 ohms. Okay. And this one is the current we just found, which is the 10 milliamps. So if you multiply by them, then you get 10 volts. So you get back to the only, so the voltage across the resistor is the same as the voltage, that is the biasing voltage, which is a 10 volt. Are you okay with that?
Yes, sir.
Okay. So practical diode model, first approach. So he's saying that if the diode is an ideal diode, it means the forward voltage is at 0. That means the diode will conduct at 0 volts. That is what he's saying. Have you seen VF? Have you seen this part? Can you see this part?
Yes.
Good. So it means it will
No,
conduct.
the screen is gone.
The screen is
You
gone.
can't see the screen. Oh, it has come.
Oh, okay, good.
It has come.
Okay, good. So VF, okay. So VF is 0 because it is ideal. So the ideal voltage, the forward bias voltage is 0 for an ideal voltage. You should put that in your mind since you are going to write MCQ. Okay. Okay, good. So that is why for forward bias, so forward, this thing is 0. Okay. But he's saying that if the voltage is not ideal, the diode is not ideal, that means it's not ideal diode, then it's a practical diode model. So if it's a practical diode model, it means there will be losses. So that means whatever voltage you are sending at the vein bias, that voltage will have a particular loss, okay? We call it the breakdown voltage, that forward bias voltage. So for forward bias voltage for a transistor is 0.7. It means that if you do not give it, if you have maybe 10 volts and you are giving to it, if you give it 1 volt, it will be, there is an opposition voltage within it, which is 0.7, that you must overcome. So once you overcome this 0.7 volts, you have one volt will remain only 0.3. Are you okay now? You understand what I'm saying? Okay. Let me see if I can bring Abu back. If his place is a bit okay, so I can also speak. Okay. So let me unshare and okay. Abu, you can unmute your mic. Your mic now. Yeah, okay, good. Okay, good. So
I was asking, hello, please, can you hear me?
yes, I can hear you.
And I was asking for the practical algorithm. Is it 0.7? Is it constant?
Yes, it's constant. It's constant. Yes.
It's constant, okay. As compared to that of 0, okay.
Yes, it's constant. So for silicon, every this thing have its own. Silicon is 0.7.
Silicon, for silicon, eh?
Yeah, silicon is 0.7. So germanium has its own. I think germanium is 0.3.
Is it 0.93 or 0.3?
Germanium.
0.93.
0.9. Silicon is 0.7. And germanium is 0.93.
Yeah.
Okay. And so each of them, each of them have its constant.
Okay.
So that's a practical model. So we're saying that if the diode is a practical model, that means that diode, before you can work, you have to first subtract the forward bias voltage, because here is not 0. It's 0.7. You have to subtract it from it. That means if you give it 10 volts, there is 0.7 voltage that you must overcome before it can conduct, because a diode is a semiconductor. You know that. You know a diode is a semiconductor. And semiconductors, they at one point, it's not a conductor, it's an insulator. So before you can make it conduct, we have to break the insulating property of the diode before it can conduct. Is that not it?
Yes.
So so for a silicon, you need 0.7 volts to break the insulation property before it is allowed you to conduct. So you've been working in electricity companies, then you know that if you are using a plastic, if you are putting a rubber in your hands to touch electricity, if the rubber insulation is not strong enough, then the insulation can be broken down, and you can be feeling small shocks. Is that not it?
Yes.
Good. So that insulation of the rubber, it has a particular voltage property to break it down. So at 0.7, that is when it will allow you to break down the insulation and allow the diode to conduct, for it to become a conductor. That is why it is referred to as a semi-conductor, between conductor and an insulator. Okay. Okay. So for the practical, then you have to subtract. So the formula for practical. So if you are using a practical diode, so when the question is asked, check whether he's saying it's an ideal diode. If it's an ideal diode, then VF is 0. So always keep this formula in your mind. This formula here.
Yes, sir.
Okay, well, so if it's an ideal diode, then VF is what? Is 0, right?
0.
Good. And 0 minus anything is the same thing. Okay, so you put 0 here, then you do your work. But if it's not an ideal, but it's a practical, then if it's a silicon, then you use the forward bias voltage of the silicon to do the calculation. So here, he's subtracting 0.7 from it. Okay, good. So when you subtract 0.7 from 10, then you have what? 9.3. And this is 1,000. So if you divide 9.3 by 1,000, that will be what? 9.3 milliamps. Are you okay? Why it is so?
No.
Okay. This is the formula now. Now, because it's a practical diode, the formula becomes this, because you have to subtract the breakdown of the forward voltage from the biasing voltage. You have to subtract this from this. Are you okay for what I've just explained? Abu, are you okay now? Okay, good. So,
yeah, I'm okay, sir.
Okay, good. So when you subtract this 0.7 from 10, then you will get 9.3. Okay, and 9.3 divided by 1,000. You know, when any division of 1,000 can be called milli.
Milli, yeah.
Yeah, that is why, and you know, it's volt divided by ohms. So if you divide voltage by ohms, then your answer must be what? Amps. Have you seen? If you divide voltage by ohms, then your answer must be amps. Okay. So you just write 9.3, then the 1,000 is represented by M. That is
because of the current.
Yes. So it's current now because it's voltage divided by ohms, so you get current. You get it. And the unit for current is amps. So if it's 9.3, you can assume the 1,000 to be milli, and the unit for current is amps. So that is why it's getting 9.3. So are you okay now?
Yeah, okay.
Okay, very good. Now you look for the vein limit. So the vein limit is simply the IF times the R limit. The vein R is the voltage across the resistor. So the voltage across the resistor, okay, because there's this current, it's in series. So you multiply this current by what? You multiply the current, yes, by the resistor, which is the 1000 ohms. And that will cancel the M and give you 9.3 volts. So you see, for an ideal diode, the forward bias voltage is different from the voltage drop in the resistor. Can you see that? Can you see that?
Yes.
Okay, good. So let's continue. Okay, so now let's go to the next side. Okay. Okay, good. Then we have something we call complete diode model. So in the question, you have to find out whether it's an ideal diode, it's a practical diode, or it's a complete diode. Are you okay with me? Okay, so if it's a complete diode, then you have to use this formula. You see that it's the same formula, only that this has been added to it. Okay. Hey, where you are, your noise is coming again. Should I mute you again?
I'm in a vehicle.
I know. Okay, so let's continue. Okay, good. So what has been added is the RD. So what is RD? So if you check, this is our biasing voltage, and this is it. So Abu, let me mute you again, then I'll bring you back.
No, you continue. I'm listening.
Okay, good. Okay, let's continue. Okay, good. So you see, this is the biasing voltage. This is the forward voltage. This is the resistor, and this 10 volts here is the RD. Okay, is the RD. That is the RD. So for the distance, you have to add the RD to this one before you can do the calculation. And you all know that the biasing voltage, which is 10 volts, is the same as the RD. Have you seen that they are the same? Have you seen that this and this are the same?
That one is not clear, please.
I'm saying that for the RD, okay, you have to add this RD to it before you can get. Okay. So this RD that you get here is the same. That RD is the voltage. Okay. This RD here is the voltage here. So the forward bias voltage is repeated down as an RD. And you add it to the limiting resistor if it's a complete diode model. Okay, that is how you work it. So when the question is asked, you have to check whether it's a complete diode model, or it's a practical diode, or it's an ideal diode. Okay.
So how will you know? How will you know this question is a complete?
He will state it. He will state it.
Okay.
He will state it. He will state that. I assume the diode is a complete diode mode. You will say that, or assume the diode in the question. Yeah, to be stated in the question. Assume the diode is an ideal. Assume the diode is a complete. He will state it. Okay, let me show you how some of the questions are framed. Okay, It's unfortunate that we do not have more time for the message, but I think you'll be able to do more before you write your exams. So let me unshare and show you something. Let me see. I think this one will do. Okay. Can you see my screen now? You can see. Can you see my screen now? Okay, good.
Yes,
Okay, good. So this is an example of how questions are set. Okay. Can you read what I've shown? The question 1.
If a transistor is not biased properly, it would work inefficiently.
Very good.
It
Produce distorted signal. Very good. So this is how questions are asked. Okay. So the answer here will be what? A. Okay.
Inefficiently.
Yeah. And here, say a transistor is biased either with the help of. When we are looking at how to bias the diode, what were we using? Is it battery? Right. And we're also using a circuit. Is that not it? It was either forward bias circuit or a battery. Is that not it? So it means both of the above are right. Are we seeing? So it means both of the above is right. Okay. Let's go to this one. Question 3. Which of the following changes in the so here is talking about transistor. Let me see where there is a okay. So you see, when a question is asked, let me unshare this one and share another one. So you see, when a question is asked,
Isabella. Yeah.
So when a question is asked, whatever you need in the question will be put in the question. Okay. Whatever you need in a question will be given to you in the question. Okay. The DC current gain beta of a transistor remains constant at 100 at 25 degrees Celsius. The base current IB. You see that everything you need has been given in this question. Can you see it?
Yes, sir.
Good. So that is what I'm trying to let you find out. Okay. So whatever you need in a question will be given to you. So we can go back to what we were doing. Okay. Okay, good. So I'm saying that in this formula, use the biasing voltage, the value of the biasing voltage. Just replace it here at the RD.
We are using the driver.
If it's a complete diode, model, then in the formula, just whatever you write here, forward bias, just repeat the same thing here. Then you follow the same model to determine the VF and also to determine the VR. That is the voltage across the resistor. Okay. Are you okay now?
Yeah, okay.
Okay, good. So let's continue. Okay. Okay. So we are going to look at a diode circuit. Okay, calculate the current flowing through the diode. So this is a diode circuit. So you can clearly see that with this circuit, this is earth, right? It has been earth. So the positive side is going to number 1. Okay, and the negative side is going to number 2. But if you look at that, have you seen this line here? That line is a cathode. Anytime you see a diode, a diagram, have you seen this line? Can you see the line? Can you see that line? Hello, Amos, can you see that line?
So I'm not with you.
You can see?
Yeah, I
Yeah, I
can
can't
see.
see.
Okay.
No, no, book.
Can you see the screen, Abu? You can't see the
Yes,
line.
sir.
Okay, let me change the color marking.
Yeah, I can see it now.
Can you see this line? The one I've marked
I'm
red. Okay, good.
The Diode Circuits, yeah.
Very good. That line is
No,
that
yeah,
line
I've
means
seen it.
that is the cathode, the negative terminal. Okay. So anytime you see a diode, where that line is the cathode, the negative terminal. So it means with this diode, the number 2 here is the negative terminal, the cathode. That is number 1 is the positive terminal. So this connection here is what? Why can we call that connection? Because check the battery and the diode. So why can we call this connection? Is it forward or reverse? Is it forward or reverse? Hello, is it forward or reverse? Positive to positive, because we said where the line is the negative. And check the positive of the battery. The positive of the battery is connecting to 1. Is that not it?
Yes, sir.
And 1 is positive, so it is what connection? Forward.
Void.
Yeah, it's forward biasing. Okay. Good. So you say calculate the current flow through the LED. So you see that there's this one here. We are using light emitting diode. The diode that we are using here is not a silicon diode. You see that the diode we are using here, this is the symbol for LED. That is light emitting diode. Okay, light emitting diode. That is LED. Okay, and it says the color of the LED is what? Red. LED is light. It's a light, so it can be blue, green, red, yellow. Are you getting me? You are getting me?
Yes, sir.
Okay, good. So you say you should calculate for the current. As usual, this is like Ohm's law. So if you want the current across this, it's all because what can you do? It's just dividing this voltage by the resistor that is across it. Is that not it?
Yes, sir.
Okay. So let's see how that is done. Okay. Okay, so we come here. Okay, so the value, so he's saying that determine the current I in the circuit. Assume the diode is forward bias conducting. That VD is 0.7. Okay, so with this,
Yes,
so he's saying that the diode, this VD, assuming the VD, that is the voltage across the diode is 0.7. Okay, that is, so he's creating some assumptions here. Okay, and here when it's a ZENER diode, so if it's an LED, you can calculate the current flow through the LED. Assume the LED is a silicon diode. So he's saying that. Hello.
Yes, sir.
Very good. So he's
I have
saying.
to set off.
Yeah. Okay.
I have to leave.
Okay. Okay, yeah, you set up and you join on your distance. Right?
Yes, I'll join. Yes, I'll join the car. So we are still going. Yes, continue.
Yeah.
Because of the traffic on the road.
Yeah, you
Well,
have.
are you in a commercial vehicle?
No,
You are in a commercial vehicle, or you are using your ride?
I'm using the right. Yeah.
Okay. All right. Okay.
So maybe I'll meet you.
Okay, so that you meet there. So you see, you say if it's LED, assume the LED to be a silicon diode. So if you assume it to be a silicon diode, then the forward bias will be 0. What? The VF will be 0.7. Is that not it?
0.7.
Yeah, if you assume it to be that. Okay. So it says a diode circuit. Determine the current I in the circuit. Assume the diode is forward conducting. That means it's a forward conducting. Then you can do the same process that we use. Determine it. So the biasing voltage is what is called VDD. So VDD is the biasing voltage. And the voltage across the diode, that is VD, is the same as the forward voltage. So I'm saying that this one, I'm saying that this one is the same as VF. And this one is the same as V biasing. Are you okay now? You are the same. Are you okay?
Yeah, go ahead.
Okay,
Yeah.
good. So let's continue. Okay, so a ZENER diode. So
Hello,
they
Amos.
say, Amos was saying, I think he will join. Okay, so the ZENER diode. So he's saying that if this is a ZENER diode, then how do you go about it? So in the circuit below, the 10-volt ZENER diode can maintain regulation over a range of currents. Varies from 4 amps to this. Calculate the range of input voltage for which the diode can maintain the regulated voltage. So he's saying that. So here, he's saying that this is a ZENER diode, right? And the voltage for the ZENER diode is 10 volts. That is the voltage across it. Okay. And if you can see, it's connected parallel. It's connected parallel to the applied voltage, which is the biasing voltage. Okay. So it's connected parallel to it. And so because of that, this, you see that this is an arrow across a voltage, a battery. If you see an arrow across a component, what do you think they are trying to say? Yes, Abu. If there's an arrow across a component like this battery, what do you think they are trying to say? Like this one. You see the arrow. Have you seen the arrow across it? Have you seen the arrow across it? Yeah. Very good. It means it's a variable voltage supply.
Yeah, I've got the voltage, the supply voltage.
Yeah, it means it's a variable voltage supply. That means the voltage can be increased to 1, 2, 4, 5. Like you can increase or decrease it. Are you okay? So it's a variable supply voltage. So you can vary the voltage.
So the voltage is not constant.
Yes, it's not constant. It's not constant because someone is varying it, not because it's self-changing, but because someone can be there to be changing it. You're okay now?
Yeah.
Okay, good. So let's continue. Okay, so he's saying to do that calculation for what we just saw. VR, if you are determining the voltage across R, okay, you see that the I is in series with the applied voltage. So it means one VR, it means IS. IS is the current that was input into it according to the instruction that was given. Okay, that was IS. Like for instance, let me go back and show you that IS. Okay. It says the current flowing through. The question is saying the current that is flowing through. So the over of current varies from. So this is it. Or what is it? Let me take it there. So good. This 4 milliamps to 40 milliamps. Okay. Why is it so? On this side, 4 milliamps to 40 milliamps. Okay. So that is what I mean. Maybe let me use the spotting. Okay. Okay.
See why the network is not stable at all.
It's not stable. Okay. Good.
So manage it.
Yeah, Amos, have you set off?
Yes. Yes, I'm set off.
Wait for me at Atomic Junction.
Where?
Atomic Junction.
Atomic Junction, okay, I'm coming. Okay. Atomic Junction, okay, I'm here.
So wait for me there. All right.
Okay. So let me go for my distance. I wanted to use the highlighter. Okay. Okay, good. So we are saying that I will start from 4 milliamps according to the instruction. So it means I start. So IS simply means I start. Because the current is going to be changed. As you increase the voltage, the current will be changing. Do you agree? Hello?
Yes, sir.
Okay, good. Because, so I start. That is why it's calling it IS. Because it's I start.
Yes.
So it's starting at 4 milliamps. So as starting, if you want the voltage drop in the resistor, then you can multiply the starting current by the resistor. Okay. And that resistor is 1,000 ohms. So the voltage drop across the resistor will be what? 4 volts. So that is the calculation he has done here. And he's saying V in. When he says V in simply means that the voltage in the ZENER voltage, the voltage in the ZENER diode, plus the voltage in the resistor, that will give you the applied voltage. Do you agree? Let me go back to the circuit and show you something. Go back to the circuit and show you something, okay? Okay. I want you to observe the circuit clearly. You see that this diode is in parallel with this resistor. Is that not it? Is that not it? Can you see that? Hello, Abu, can you see it?
Yeah, it's in para.
Yes, in para. Okay, so for a parallel circuit, the voltage is divided among them. For a parallel circuit, the current is what? For a parallel circuit, because this is in para, have you seen it? Oh, sorry, check again. It's in series. It's in series because current flowing through here will come here straight forward. So it's in series, right? Check the circuit again, it's in series. Because if you move a current through this one, it passes through resistor, it gets here, it cannot go here. It has to come down here to the ground. And it moves from the ground to join the negative part. So it's in series. Can you see it's in series? Are you okay that it's in series? Hello, Abu, are you okay?
Yeah, I'm not yet confused.
I'm saying that.
So where do you start the current? I'm looking at the current direction.
Yes. Just
The direction of the current.
assume a direction for the current. But current always flow through the positive side of the applied voltage, which is this side.
Yeah.
Okay, good. So because of that, current will flow from
true.
here to this resistor. Then it will come to this junction. Then it have to come here because it cannot go to the other side, to the ground. If it flows to the ground, that means it can join through the ground to the negative part of the battery. So it is in series.
Okay.
So the circuit is actually in series, not in parallel. Okay, very good. So now that we understand that point, that is in series. So it means that for a series circuit, current is what? Common, because it will flow through all of them. But the voltage is shared among them. So there will be a voltage drop here, there's a voltage drop here. So the question is saying that the voltage drop here in this ZENER diode is 10 volts. So if the voltage drop here is 10 volts, and to find the voltage drop at this point, you multiply the minimum current, the starting current is 4 milliamps, by this resistor. So if you multiply by it, you can get the voltage drop here. So if you want V in, which is the biasing voltage or the applied voltage, then all that you have to do is that you have to add this 10 volts to whatever voltage you get for the resistor. Are you okay with that?
Yes, sir.
You add the voltage drop here, that is VR plus VD. If you add VR plus VD, VD, okay, and this is VR. So if you add these two, VR plus VD, then that will give you what? V in. Just add these two. Are you okay? Are you okay?
Yes, sir.
Good. So when a question like that is given to you,
Go
all
ahead.
that you have to do is that pick the starting current and use it to multiply the resistor. So once that is done, you will get the voltage VR. Then once you get VR, this has been given to you. So you add it to VR, then you can get V in. Okay, so let's see how he go by it. The same way as I'm explaining. Okay. So we move forward. So V in this question, you see that V in is actually VR plus VZ. And VZ is representing ZENER diode. So it's the same as VD or the V of the diode. You're okay with that, right? So that will be 4, because if you do VR calculation here, you get 4. So that will be 4 plus 10 volts, which is equal to 14 volts. Okay. So this is the minimum input voltage. Okay. When the voltage is minimum, the current is 4 amps, 4 milliamps. So what about if the voltage is at 40 milliamps? Okay, the voltage is maximum. So I think this English here is a mistake. It's not minimum, but it's supposed to be maximum. It's a mistake in the slides, okay? Are you hearing me? Why is he doing that? Are you hearing me?
Yes, sir.
I'm saying this minimum here in the slide say mistake. It's supposed to be maximum. You do minimum and you do maximum. Okay. Good. So for the maximum current will be 40 amps. So because he said the current is changing from 4 milliamps to what? 40 milliamps. So at 40 milliamps, that will be the maximum applied voltage. Are you okay now? So if you want to determine that maximum voltage, then it will be VR plus VZ. So at maximum voltage, what was the voltage drop in the R? So you multiply the 40 milliamps by the resistor. You multiply the 40 milliamps by the resistor, and that will give you 40 volts. Then you come and add the 40 volts to the 10 volts, and that will give you the 50 volts, and that will be V in. So I hope you can clearly do the calculations if similar questions come in your exams.
That's true.
Can you do?
Yeah.
Okay. So you have to check whether it's minimum or maximum. Then you know which current to use. Okay. So let me go back to the question for you to also have a look at something again. So check the question again. If you check the question, he's saying that in the circuit below 10 volt ZENER diode. So the ZENER diode voltage is 10 volt. That is constant. So this is this 10. Okay. It can maintain a regulation over a range. Do you know why the ZENER voltage is doing a regulation? Have you seen it's doing a regulation? So you understand the meaning of voltage regulation? Like a fridge regulator. Do you know the one we buy for our fridges? The binatone regulators we buy for our fridges. I hope you have seen it, right? Hello, Abu. Amos, are you there?
Yes, I was.
Good. I'm saying the binatone we buy for our fridges. Regulators. The major component in it is a ZENER diode.
Oh, okay.
And so he's saying that they are using this as a regulator. Okay, that means it's giving you maybe a constant voltage of 10 volts.
Okay.
That is the regulation is doing. So that is why the voltage has been maintained at 10 volts there. So it's a regulator to give you a constant voltage. That is a work of a ZENER diode. ZENER diodes are used as regulators to ensure we get a constant voltages. Okay. Good. So he's saying that it's starting from, so the regulation ranges. You can start it from 4 milliamps to 40 milliamps. So that means at minimum applied voltage, the current will be 4 milliamps. And at maximum applied voltage, the current will be 40 milliamps. Are you okay with what I've just explained?
Yes.
Good. So when a question like that is given to you, if you are doing the minimum calculation, you can say find the minimum V in, or the minimum applied voltage, or the minimum regulated voltage. Okay. If he says that, then use the minimum current and multiply by this resistor, because they are in series. And in series, current is common. So you can multiply the minimum I, that is the minimum I, by 1.0 K. That is 1,000 ohms resistor. No? Okay. So once you do that, then you just add, because this is a series circuit. In a series circuit, voltage is added because they share the voltage. Current is common in the series circuit. So I here will be the same as I here. Because current is like pouring the water in a pipe tube. Is that not it? So if you pour the water in a pipe, it will flow here, flow through this one, flow through this one, flow through this one, and come back to the source. So if it's a series circuit, the same water quantity will flow through the pipe. So that will the same current flow through them. Okay. Can you hear me now?
Yes.
So that means the same current will flow through them. So in a series circuit, current is what? The same. But voltage is shared. So it means if you want V in, then you have to add the voltage drop here plus the voltage drop here before you can get the V in. Are you okay so far? So the minimum, you use this. For the maximum, you use this. So the maximum, you use it, and the minimum, you use this. Are you okay? Okay, good. So now let's continue. Okay. Okay. Yeah, hello.
Yes, sir.
Okay, so the tutorial that you gave to me for basic electronics, who gave you that tutorial?
Sir, I'm the one.
Yeah, I'm saying who gave that to you?
Is the
The instructor, the lecturer,
no, lecturer, yeah,
the lecturer who is teaching you.
yes, that's
Okay, good. So that is the one he has given us. So it ends there. So if it's the one who gave you that, maybe the next time will come from that one, right? And it's ending here. So I'm hoping that maybe questions will come from just this ones because the tutorial ends here. So you can go and ahead and maybe once we have gone through, so you have the slides with you, right?
Yes, sir.
You have this tutorial slides with you, so you can go ahead and be reading to and be checking out when you are about to start exam. I'm hoping that after your midterms, we have more time to do more for you to be very good, so that in the exam,
yes, sir. Well, get more time.
yes. Okay. So
Yes,
you can
more
do
time. Very
That's the
important.
best class.
Okay, so it says okay, so you can do your own revision small so that you can prepare for your exams. Okay. If you have any challenge during your
Hello, Mr.
lesson,
Busi.
yes.
Please, I'm not yet registered though. So I mean, but Tokoko asked me to send him the payment and the pay receipt. I'll
Yes.
send it to you. I don't know why.
Yeah, you should go with your receipt.
So if you can,
Are you going
yeah,
with
ask
your,
me to send to his WhatsApp.
I'm saying, are you
It's
going with your receipt?
right now. Send it.
Are you listening to? Are you going with your fees?
No, I have it on my phone.
Okay, that is okay. So don't worry. I'm saying if someone comes and say you have not registered, just tell them that you were having a challenge with your email. So you came to UITS and they reset it for you. By the time they reset it, the registration is over. So they ask you to send it to your examiner. So you have sent everything to the examiner. So you do the registration for you. Okay. And when you are writing your midterms, you write your name and use your student number. And you just if you use your student number and you indicate you have not yet received your index number. Are you okay? Your ID cards are not be given to you, right?
Yes, sir.
Good. So that is what you have to do. So you use your student number, but so when you write student number, then you write into bracket student number that indicate that you are using your student number. I hope by the time you write your exams, Dr. Poku might have registered you so you can have access. Okay. Hello. Is anybody hearing me? Because it seems nobody is talking now. Amos, your mic is mute. Okay, bye-bye. Let me stop.